blockchain in data sharing and sales. So this is actually really another kind of really good use for blockchain, right? Data sharing and sales. So basically data sharing as a service, and it's basically introduced by IOTA, a distributed ledger technology developed by the IOTA Foundation. And again, it uses the blockchain to share or sell unused data. And data is all over the place. We have IoT devices, we have cell phones, we have location data, we have tower data, we have weather station data, we have just about everything. Your car generates data. And those unused data bundles of enterprises could be routed to places that need it the most. So one of the projects I worked on, I thought this was kind of interesting, was a smart road project in Virginia, and tying sensors to streetlights, and then bringing that all forward so that your car and those street posts could share data back and forth. There's a lot of unused, but very cool data about how traffic flowed in the areas where we put sensors. That kind of data could help people that are trying to figure out how people move around a city, could figure out how people do bus routes, could figure out how product moves around a city. It is an amazing pile of data that basically got thrown into the trash can when we were done because we couldn't figure out what to do with it. All right, we didn't need it anymore. Someone else could have used it, but blockchain can be used to, basically as a marketplace to store and forward that kind of data to improve a host of other industries. And that's why this IOTA Foundation is really kind of an interesting prospect on this. So one of the largest obstacles preventing the full fulfillment of big data is that there's too much data. The other problem is that it's locked in data silos. In healthcare, you kind of see that where it's all between Epic and Cerner. You see data that's stored in silos at Microsoft or Sony for gameplay. And that the way they meter and measure people inside of a game is this amazing environment of data to model how gamers actually play. That's a really interesting chunk of data that could go back to how do people problem solve, right? It's not just who caught the boss monster, but it's how did we solve the puzzle. Right, if you were able to measure and meter how people solve puzzle games or MMORPGs or first-person shooters because you are really solving problems, that's some really cool data that could really help out a lot of people, but it's in a data silo and they're not going to be shared. It's out of here. We're not going to do it. And a loss of just wasted data, and what they're saying by McKinsey was that 99% of all this data is just wasted. It's just chucked into the bin and no one cares. It could really potentially contain extremely valuable information, but we don't really know what to do with it. We don't really know where it works, and we don't really have a way of creating a public, open, decentralized data lake that anyone can access as long as they pay for the access. Just don't have it. So data trade. Data trading is a really interesting process because it can take a lot of the waste out of what we're doing. You may collect data for one central thing, but that data actually ends up being really kind of interesting. So we collect the census data every 10 years. What's interesting about that is it can really tell us how different places in the country are growing or not growing. That's really good data. But you have to fish through the census data and you have to run the blocks and you have to do the rest of it. And that kind of migration data may be run 20, 30, 40, 100, 200 times because it's interesting. A lot of people may use it. Wouldn't it be cool if we could just hand them that one data set? Oh, you're interested in migration? You're interested in population growth in this zip code? Boom, here's your data. Here, $10. And call it good. And all that kind of stuff can be stored as pointers in the blockchain. And that would really help break down the grid log and allow big data to become truly big data, as long as we can guarantee some certain amount of anonymity in what people are doing. You know, you don't really want to necessarily know just how bad I am at Call to Duty. You really don't. Right? I would want that data anonymized because I don't think I've even gotten off the landing pad in Call of Duty. Right? So a major cause of the fact is why data sharing is becoming cheaper. It's really expensive to sell fine-grained data without it or being pre-processed. Right? And not only that, there's a lot of red tape to get to a single data purchase. You don't even know who owns the data. Now, the cool part is that this is making real-time data all but impossible, but this can be solved by using the blockchain, and that's where this is kind of neat. You have your pre-digested data, you're selling it, you're doing cool stuff with it. There's going to be a lot of data generated by Internet of Things devices, your weather stations, your cars, all the things that have an IoT component, which is just about everything now. So I would love to have a data set from Tesla on how people actually drive Tesla cars and how they actually use the self-drive versus manual drive versus all the things that are going on inside that car as someone is making a road trip of more than 300 miles. Tesla could probably provide me that data relatively quickly and relatively anonymously for a price. Now, it would be really cool if Tesla could provide that data to everyone for that price. They could do this and do this as a data trade. Trading data is a really important thing, but that authenticity of the data, making sure that it's really coming from Tesla or Microsoft or Sony or whoever you're buying it from, is actually the person that made the data or the person that's authentication for that data that actually has that data is generated. It's not black market data, because there's some really interesting black market data in there if you've ever gone into the dark web and you go into the marketplaces. Black data is things that have been hacked out, your social security number, all the other things that went along with that. So as long as you are making sure that data is authentic, you can do a lot of things, including removing man-in-the-middle attacks, data tampering, and the data is only going to be as valuable as it's valid. So you just want to make sure that your data is coming from a reputable source, that the data is not garbage, that it's clean, you can actually do something with it, and then that you're not having data tampering going along with it, because you don't want to make a good decision based on bad data. So IOTA. They've come up with a system called Tangle. And I actually think Tangle is really kind of an interesting process, because what they're calling it is a directic acyclic graph. So every transaction or data transmission validates two previous ones. And it's really just a big pile of spaghetti in the end. But it's a tree that you can still move around. It's still a tree that you can go ahead and process as a regular blockchain architecture, go into the block, go into the packet. There's probably going to be some sizing issues. There's probably just going to be pointer issues because you're not going to shove a lot of data into the actual blockchain. It's going to be pointers off. But it'd be interesting having that gigantic worldwide viewpoint into how data movement works, data fees on transaction and data transmission. So you can remove that real-time payment obstacle, find granular payment obstacle. It's all going to be there. You can find it, go pay for it, and move. And you're not really doing anything. You're really just traversing that blockchain, trying to find the data that makes it interesting for you. So there are some concerns tied to data training, right? Because we want to make sure that the data has got some integrity to it. Again, authentication, that hasn't been altered or hasn't been tampered with. But the entire design of Tangle means that the entire network remains decentralized. So unlike blockchain architectures which centralize around mining farms, which further centralize into mining pools, Tangle moves around a little bit different, right? Tangle actually takes a look at the data in a completely different way. So Gossip and MAM. At its core, IOTA uses the Gossip protocol to propagate transactions through the network. This mechanism means that any data with sufficient weight can be dispersed all the way across this cluster efficiently. Transactions carry value or data sent from a car, cargo ship, anything. It all goes through that whole process of making sure that that transaction is propagated through the network. Then there's another part, masked authenticated messaging. Second layer to the data communication protocol. So it adds functionality to emit and access the encrypted data stream, right? So you may have things like RSS coming off of a blog site or something else. So a lot of our communications are now encrypted because they have to be. Because that way they're not man-in-the-middle attacked. So you're using Tangle, that distributed ledger, regardless of the size or cost of the device. You add that consensus protocol to these messaging streams, and given the properties that MAM has, that masked authenticated messaging, it will meet the industry's need for integrity and privacy. So again, these two things, Gossip and MAM, basically are the underpinnings for Tangle. So it's a neat process. And then there's messaging. And IOTA, a user can publish a message at any time. They only need to conduct a small amount of proof of work to allow the data to go through. So that could be a problem for the 51% attack, but this is necessary to prevent a full spamming of the network. If the nodes are listening to the channel ID, the message is gossiped through the network will be received by the subscriber when it reaches the subscriber's node. So we know that there's some manipulation that can happen here. We're going to go ahead and do a little bit of proof of work to make sure that data will move through the network, to make sure that in a lot of ways it can't be spammed. But we also understand that there's going to be some risk here. There's going to be a problem with 51%. There's going to be a problem with a couple of other kinds of attack modes, data tampering and data altering. So the size and type of the messages inside of that process. So I will send a message from mine saying this data is available now. you can actually have any size. You can actually give a good description or a small description depending on what you've got, right? So you can evaluate and demonstrate that smaller messages have a higher potential for data integrity. Again, problem solving, right? So you could transmit the full encrypted 4K video, or you can do a link, a pointer to it. And I think, again, a lot of the things that you see when you are looking at stuff like this, you're looking at things like smart contracts, you're looking at identity, you're looking at other things. What goes into the blockchain is really more of a pointer to the data rather than the actual data itself, unless the data itself is easily formatted and transported in the blockchain. So more efficient to use, MAM signals some off-Tangle protocol for the actual streaming of that video or whatever you've got going. So those messages are part of the distributed ledger. You can then go back and track down that video or that data point or whatever you need to make sure that it's still there and that you can actually use it. So these messages then, being part of the ledger, contribute to the security of the network by increasing the total hashing power. Again, we're going to use that whole hashing process where you benefit from data integrity properties of the network. That's the other good part about this whole thing. Then MAM and Merkle Trees. So MAM, masked messaging, uses a Merkle Tree based signature scheme to sign the cipher digest. So we're all used to that there. That's all really common blockchain kind of thing. So the good part is that the Merkle trees uses the ID of the channel. So you can have multiple channels, and you can have multiple Merkle trees that all intersect with each other. I may be interested in weather station, and then I need to tie together some weather station data with some geography data and other kinds of data along the way, transport data. So how much does the weather alter transport patterns in Denver, Colorado in a snowstorm? That would allow me to search all of the channels that are available to me for that. And then we could actually then turn that into a running data project that would then start its own channel ID and its own Merkle tree that ties all that stuff together. And that's why it's really a tangle. You can do a lot of weird things with it that make it more interesting in terms of how you want to do data pooling across multiple sets of data. And then there's security. Each message is encrypted with that one-time pad that consists of the channel ID and the index. Right, so that's another way. We are going to do an additional nonce that may be used as a recoverable or revocable encryption key. So pretty standard. We're all used to this with the blockchain now at this point. The encrypted payload, the signature, leaf siblings, all of that's published to the Tangle. So anyone knowing the symmetric key can find it and decrypt it. We're good to go. We've been here. We know that this all works in blockchain. We all know that this works well. We just need to make sure that when we're consuming that stream, that the message is first authenticated by validating the signature and verifying the signature belongs to one of the tree's leaves, and then you're good to go. Right? If the signature verification fails, the entire message is deemed invalid. And that gives you some really good point source support for understanding where all this stuff is going to go and whether that data is authentic, whether the data has been altered or something else along the way that you want to do. Then there's what's interesting on this one and the Tangle is that public or private mode. So you can actually have public data. Public mode uses the tree's root as the transaction the message is published to. So anyone can stumble and decode it, you're good to go. Similar to basically radio. Anyone can listen to the radio. Then there's private mode, which is going to be more like your encrypted radio stream. So direct radio to your car. Private mode can be encrypted streams not meant for public consumption. You could shove some FOU data in there, some restricted data in there, depending on how you want to do it. In private mode, the hash of the Merkle root is used as the address, and basically it stops a random user from decrypting your message if they stumble across it. And again, they're not going to be able to derive the root, so this makes the MAM stream only readable by those who are provided with the root. So more similar to that encrypted radio stream, anyone can see it, but only those that can those have it can decrypt it. So think of your Comcast or your Rogers Cable or anyone else that has that kind of process. Same thing. It's a neat process. You have data that can be public or private. Then restricted. Restricted actually really kind of like this one, Mark, because it makes more authorization responsible for that private mode. So you can actually used to address the network and the hash authorization of the Merkle root. So the message publisher can stop using the auth key without changing their channel ID, right? That is the Merkle tree for whatever you got streaming. So access could be in a sense revoked from subscribers if desired. So a key change event occurs when a new auth key needs to be distributed, and you can actually make it so that you can go from public to private or restrict that data set depending on how that data set is being used. So neat stuff. Then on top of it, you can also split the channel. And that means that future messages can use that new Merkle tree whose root has not been revealed before. So you can do offshoot channels. You can do specific subsets of data. You can do a lot of other things that go along with that. As long as you can permission the data and providing that fine-grained access, you can just really go all over the map with your data trees. This is great if you're doing a lot of interconnection data. If you do things like peptide research, if you do things like genetic research and other things like that, there's a lot of things that are going to split all over the place depending on what you've got. So again, neat idea that IOTA has here. And then finally, what does the weather channel do? You know, you've got weather station sensors. They're all over the place. You may have weather, you may have soil, you may have air quality, wind speed, all that stuff. All of these are individual streams. You know, if you wanted to make a weather direction map of the United States, you could go in and do that with all the wind directions and everything else and track it over time. Kind of watch how that will all work. That's the power of this IOTA Tangle, is that it actually gives you the access to all that kind of data that you can just hammer it out as you go through. Now, if you add in smart contracts, right? I mean, again, we keep on building on top of all this stuff. Smart contracts can bring scalable and flexible buying and selling of data into the IOTA ecosystem. So allowing anyone to spin up that smart contract, author it, sell the data, and make some money. And that will allow multiple blockchains to anchor to the Tangle to solve some problems with smart contracts that go along the way as well. So neat stuff. And then finally, code. So the new cool part is that there's actually some code out there. You can go ahead and pull down the client libraries directly from IOTA if you want to go play around with this. It is a really interesting technology along the way. So you've got your client lib, your wallet, special purpose libraries, client libraries, and then the client libraries in different languages, TypeScript and Golang, and C for embedded devices for microcontrollers. So there's a lot of ways of making this IOTA process work in terms of how to get the data set jived up for the Tangle. And then they actually give you a really nice viewpoint on how this whole thing has been constructed across the board for your node, whether primary or secondary. You've got mainnet and devnet, communication layers. The way they've built this out, they've kind of got their development test bed, and then they've got their functioning production network. So make sure when you're building all your stuff out that you're in that devnet rather than mainnet in terms of the construction. The construction is really what we would expect to see from any other kind of blockchain identity process that we got. And then there's the code on GitHub. So GitHub, go Hornet, man, go grab it. It's an interesting code to go review. It really is really interesting on how IOTA has solved this particular problem for data brokerage. So in summary, IOTA, the Tangle, looks like an interesting way of addressing super large data pools, allowing segregation, privacy, public, restricted modes, a lot of neat things that can be tied up to provide links to really interesting data sets or links to raw data that you can then turn around into really interesting data sets. So you can pull data from silos that can be mined or links to data on the network that are interesting to people on the chain. It's still pretty primitive. There's not a lot of people here, but they're actively being worked on GitHub. So this may actually have some legs, maybe something that you actually may want to work on. Again, neat idea in trying to do data brokerage. And this is about the only data brokerage and data sharing that I can find that's going on in the blockchain right now. So that's it for this lecture. I will see you in the next one.